Good afternoon, class. It's your instructor, Gearhart. We're going to be talking about bugs today, by which I mean insects. Something like this. This isn't a real insect, but you can imagine it is. I want you to imagine that you see this insect, this bug, and he's not over here, but he's walking along the whiteboard. And you are a scientist. You observe that the bug passes through the point x1, y2, which would be right about here, and you keep watching the bug, and a little bit later you observe that the bug has passed through the point x3, y5. That's up here. Now, you observe one more critical thing. You observe that the bug appears to be walking in a straight line, like this. So I'm going to take a straight line and draw that line through the 2 points that you have observed the bug to have passed through. Now, I'm going to label them over here. The first point was 1, 2. This is an ordered pair. The first number is an x value, and the second number is a y value. The second data point that you observed was the point 3, 5. So I'm also going to label that x and y, except now I've got x, y, and xy. So what I'm going to do is use subscripts on these x's and y's so I can tell them apart. This is going to be x1, y1, and this is going to be x2, y2. Your goal is to find an equation which describes the path of the bug as it moves along this whiteboard using the coordinate system. By the coordinate system I mean the x and y axis. Now, the crucial fact in choosing your model is that I told you that the bug appeared to be walking in a straight line. So you probably want to choose a model, and by model I mean a type of equation, that has this form, which you might recognize as the equation of a linear equation or the equation of a line. Let's first of all calculate the slope of the bug. We'll do that over here and I'll erase it. I'm sure you're familiar with this. This is the point x2, y2. So it's 5 y2 minus y1, 5 minus 2, x2 is 3, minus x1. I'm using the formula for slope and I get the number 3 over 2. The slope of the line we're looking for is going to be 3 over 2. To find the equation of the line, I'm going to write down what's called the point-slope form. Y minus y1, whoops, that's a 1. Y minus y1 equals m times x minus x1. We just calculated the slope to be 3 over 2. So I'm going to fill in the rest of the numbers. Y minus, I'll use this as x1, y1. Y minus 2 equals 3 halves x minus 1. Now I'm going to simplify and put it in slope-intercept form. This is the slope-intercept form. Y is equal to 3 over 2 x minus 1 plus a 2. That negative 2 is over here. Now it's plus. Y is equal to 3 over 2 x minus 3 halves plus 2. And finally, y is equal to 3 over 2 x plus a half, if I did that all correctly. This is our model. Because the equation that we used is a linear equation, this is called a linear model. You're probably familiar with doing this, using 2 points and finding the equation of the line that passes through them, but you're probably not used to talking about bugs. I want to make a comment about some of the values. This number 3 over 2 describes how steeply the path that the bug is traveling on is. That's called the slope. When x is equal to 0, that's here, the y value is equal to 1/2. Notice that that's 0, 1, that's right about 1/2. This is called the y-intercept. It could also be considered the starting value. Now, you could use this equation to calculate the bug's y position for any x position you want, even going down here to places where you didn't see the bug was actually walking. Now, we've been studying equations in section 5.5, which are not straight lines. I want you to imagine that there's another bug. You observe the bug coming along, and he passes also through the point 1, 2. and then he also passes through the point 3, 5. If you wanted to find an equation that described the path of this green bug, and pardon my drawing, it's not very good. This should be a nice smooth curve. If you wanted to find an equation that would describe the path of this green bug, it would not be appropriate to use this model because the bug is not traveling in a straight line. So think about equations that you've looked at lately that might be this shape. Let me give you a hint. Exponential growth function. So what we're going to do now is we're going to look for a model that has this form. Y is equal to a times e to the bx. Let me make a note about parameters. Parameters are values that appear in your equation, which are not the variables. The number in this has not been specified yet, but the parameters are a and b. When we were over here, the parameters that we were looking for were m and b. M is the slope, b is the y-intercept. Linear equations like this have two parameters. There's two variables, x and y, and the two parameters. We're also looking for two parameters. X and y are the variables, and e is that thing that we talked about, exponential function base e. I'm going to give you a procedure for finding an equation that looks like this, given two data points. So I'm going to put the steps that I'm doing up here, and hopefully they won't get in the way. I might have to get rid of them. Step 1. Use two data points to create two equations of the form. This is the form right there. The two data points are 1, 2, and 3, 5. Now, keep in mind this is still x, y, and x, y. I'm going to use the second data point first, which could be important. I'll explain why. This data point tells me that when x is 3, y is 5. In other words, when x is a 3, y is a 5. So I'm going to fill in that information. 5 equals a times e to the b times 3. I just replaced the x with a 3 and the y with a 5. I'm now going to create the second equation with the first data point. This data point says when y is 2, x is 1. Now that might seem like a strange way of writing it. It's b times 1, which you could just write as the number b, but I want you to see where these numbers came from. Step 2. This may seem mysterious to you. It's not that mysterious. You'll see why. I'm going to divide the two equations and simplify. I'm going to simplify doing two things, using algebra and exponent properties that we studied. Divide the left side and divide the right side. 5 over 2, I'm going to leave it as 5 over 2. And then there's going to use one equal sign. Now, notice what happens. A over A cancels. That leaves me with this. Rewriting it slightly. E to the 3b over e to the 1b, or e to the b. If you recall the exponent properties that we used, that's e to the 3b minus b, or e to the 2b. That means that this simplifies to this. E to the 2b. This gives us a nice, simple exponential equation, one unknown. That one unknown is b. In section 5.4, you learned how to solve equations like this. I don't need these numbers right here, so I'm just going to erase those. That's still the x-axis. We're going to solve for b. I'm going to take the natural log of the left side, take the natural log of the right side. On the right side, we have an inverse property that says the natural log of e to an exponent is just equal to the exponent. In this case, that's 2b. We still have the natural log of 5 over 2 on the left side. Now I'm going to divide both sides by 2, because that cancels the 2, and that gives me b is equal to the natural log of 5 divided by 2 over 2. This value is going to be calculated on your calculator. One comment. When you divide the equations, I don't recommend reducing these numbers. Leave the fraction as it is and carry it through all the way to the end. It will make it much easier to check your work, and it will make it less likely that you make a mistake, and you'll let the calculator do the work at the end instead of you doing it. I calculated the value for B to be approximately, I'm rounding to 4 decimal places, 0.4581. This is a good number of decimal places to use usually, 4 decimal places. We're halfway there. We found one of the parameters. We found the parameter B. Now what we're going to do, what I just did was step 3. Sorry, I forgot to put it up there. Now what we're going to do is we're going to solve for the parameter A. In order to do that, I'm going to have to move over there, so I think my assistant is going to have to move the camera because I ran out of space, unfortunately. When you solve to find the parameter A, I recommend you use the equation that was in the numerator when you divided. That way we'll all get the same answer and we'll avoid round-off error. So the equation that I'm using is, rewriting it here, 5 is equal to A times E to the B times 3. I'm going to substitute the value that I have for B right there. That gives me 5 equals A times E to the 0.4581. That's a times. Maybe I should write it like a times 3. I need to solve for A. This looks really complicated, but it's not complicated at all. It involves one simple algebraic step, and that is dividing both sides by this number. E raised to the 0.4581 times 3 is just a number. You don't know what it is right now, but your calculator does. So I'm going to divide the right side by that exponential quantity, and I'm going to divide the left side by the same quantity. Notice what happens. You have the same quantity downstairs and upstairs. That gives us this. A is equal to 5 divided by exponential function base E raised to the 0.4581 times 3. Now it's calculator time. I'll show you how to type this into your calculator. 5 divided by, press second ln to get the exponential function base E, and now you need these parentheses. If you forget them, you'll get the wrong answer. E raised to parentheses 0.4581 times 3, and that's a 3, sorry. I rounded it off to 3 decimal places. The number that I got is 1.265. That's the approximate value, or the value that we're going to use for A. We now have found both of the parameters. We have one thing left to do. I'm going to write the equation down in this format because that equation is our model. And this is an exponential model. I'm just going to write the model. Well, I better write exponential there to remind us. The model is y is equal 1.265 times e to the 0.4581, and the variable is x. The two parameters, A is called the initial value. Why is it called the initial value? Let's let x equal 0 and see what happens. 0 times that is 0. E to the 0 is 1. 1 times 1.265 is 1.265. So in other words, when x is equal to 0, this y value is equal to that number there, 1.265. That's the y-intercept. 1.265. And the number that's here next to the x represents the growth rate of the model, how quickly it's growing. This is a very steep growth rate, and you can see that from the picture. The fact that it's a positive number indicates that this is a growth model. Later on, you will be using or finding models where this turns out to be a negative number. In that case, the graph will be a decreasing exponential decay function. Thank you.